Today, we want to talk about a little bit more detail about approximating a definite integral using a table. And so here we have just a generic table, and we're going to approximate a definite integral, in this case from 0 to 9. We're going to talk about the things that we can do to do this and why it makes sense to do those things. So yesterday, we weren't as formal about it. We just kind of like guessed at how it worked. And we did an overestimate, an underestimate, and then an average of those two. So we had something below what we were looking for, something above what we were looking for. It makes sense to just average the two sometimes. So in this case, that's what we're going to do. We want to think about what thinking goes behind these kind of approximations. The first thing we're going to do is just find an overestimate and an underestimate. And in this case, we're just going to say for this interval from 0 to 2, we're just going to use 10 for an underestimate or 16 for an overestimate. The thinking is that the function is constant for each of those intervals. This is a standard integral thing to do. So if we're using a larger value or using a smaller value, we're imagining the function is constant. Well, let's just put it at, we're thinking that f of x is constant. I spelled constant wrong. This is just a very large version of what we're doing when we're calculating definite integrals with area anyway. We assume that the function is constant. For the average, our assumption is that the function is linear. We go up 1 degree. We just connect the points. So when we calculate the average, the assumption is that f of x is linear. Constant is linear with slope 0. This is linear with slope something other than 0. These are the easiest things that we can do. Constant means we're assuming that things are not changing. Linear means they're changing in the easiest way possible, our default way of thinking as humans. We just connect things with lines. I've been to the universe where they connect everything. The default mode of thinking is to connect everything with circles. It's a mess. It is so hard in that universe to make one of those paranoia boards where you have all the string connecting all the things. Because our default mode of thinking is to connect with string. So it's like, I'll pin here, tie some string in between. Everything's great. We look like proper paranoid. But they're like, well, I have to connect point A to point B with like a semicircle. It's just like, they have to put pins all over the place. I'm like, oh, guys, why don't you just use a straight line? It would be so much easier. Now I got banished from that universe. So here I am. All right. So now the interesting thing that we had in the problem yesterday, I don't know if interesting is the right word. The thing that we had in the problem yesterday was that our delta x was variable. And so I've got another delta x is variable in this one. We don't have the same delta x all the way through. So we have a different delta y and a different delta x. But that's for the linear stuff. We're gonna look at this as 1, 2, 3, 4 rectangles. When we're going to do an over-under, when we're going to think that the function is constant, we're going to imagine calculating the areas of 4 rectangles. So in our overestimate, of the integral from 0 to 9 of f of x dx, the first rectangle is going to have a width of 2. The second rectangle will have a width of 3. The third rectangle will have a width of 3 again. And the last rectangle will have a width of 1. So we've got all these four different delta x's. So we have a width of, in this first one, the delta x is 2. In the second one, the delta x is 3. In the third one, the delta x is 3 again. And in this fourth rectangle, the delta x is just 1. So we have 4 different values of our delta x. For our overestimate, we're going to use the largest value that we know about the function on each of those rectangles. So for this first rectangle, the largest value that we see is this 16. So that's this, we just use 16 for that whole 2 units of x. And then 16 and 36. 36 is the largest value that we have there. Then from 5 to 8, the function has gone back down. So the largest value is once again 36. And for this fourth rectangle, the largest value is 30. This is going to give us an overestimate. We use the 36 twice because in 2 different rectangles, it was the largest value. So that's going to give us our overestimate. For our underestimate, we'll use the smallest value. Our setup is going to be the same. We're still trying to integrate from 0 to 9 of f of x into x. The first rectangle still has a width of 2. The second rectangle still has a width of 3. The third rectangle still has a width of 3. And the fourth rectangle still has a width of 1. But now we're going to go through and look at each interval and pick the smaller value. So for this first rectangle, 10 is going to be the height. For the second rectangle, it's 16 and 36, so we'll pick 16 for the height. For the third rectangle, I've got 36 and 30, so I'll pick 30 for the height. And for the fourth rectangle, I'll pick 29 for the height. We're just imagining this area as 4 rectangles. This is the low-res version of what's going on. This is the Game Boy version of what's going on. I can calculate these ahead of time. And I do not trust myself to do the calculation just by looking at it. So I have flat 2 times 16. 2 times 16 plus 3 times 36 plus 3 times 36 again plus 1 times 30. Our overestimate is 278. For our underestimate, we have 2 10s, 3 16s, 3 30s, and 1 29. So our lower estimate is 187. That's us thinking that the function is constant on each of those four, and we're making four rectangles. When we find the average, we're finding the areas of four trapezoids. So to find the average of these two, we'll take the average of our overestimate and our underestimate. $232.5. This 232.5 is going to be the area of four trapezoids. $232.5 will be the area of four trapezoids. Yesterday, the question came up is the average is the best. It's kind of the best that we can do based on this data. We could definitely come up with, if there was more data, the data could indicate that things are closer to rectangles than they are to trapezoids, in which case maybe one of the flat estimates is better. So it depends on how weird your function is. Yes. This is a slight variation of left and right approximations, because notice that I used the 36. 36 was on the right of 2 to 5, and 36 was on the left of from 5 to 8. So the reason that we're doing, I didn't call this left and right, is that the function goes two different directions. We see the function goes from 10 up to 36 and then back down to 29. When we have a function like we had yesterday, where it was always decreasing, the function was always decreasing, then left is the same as over, and right is the same as an under. But in this case, we did over under rather than left right because our function went two different directions. So we did over under instead of left right. Close enough. We did over under instead of left right because our function is both increasing and decreasing. If our function is strictly increasing, then the left approximation will be under and the right approximation will be over. Oops. Like we saw yesterday, if f is strictly decreasing, then the left will be an overestimate and the right will be under. So the left is over and the right is under. If I make this go the other direction, then just reverse it, multiply by -1. If f is strictly increasing, then the left will be an underestimate and the right will be an overestimate. So if I go from the left here, the left will be an underestimate and the right will be an overestimate. But when we find the average of the left and right, we're always making trapezoids. Yesterday, our problem, the function was just decreasing. And so we could do left and right, and that got us an over and an under estimate. In the table that we had in today's example, the function was both increasing and decreasing. 10, 16, 36 is increasing, 36, 30, 29 is decreasing. So over under is a different direction than left and right. How's everybody okay? We look super stoked. There's no class tomorrow, so that's why everybody's like happy. And it's extra because y'all don't have to be here, but I have to be here. So it's like all students with them. Now you have to show up, but we get to stay home. It's like when a teacher with an 8 o'clock class cancels the class at like 7:50. And you like get all the way out here. It's like, I'm on time for class once. And there's like a sign outside the door. It's like, oh, class is canceled. I sent out an email today at 5:30. I don't know why you didn't check your email at 5:30 this morning. Why would? I don't know. You have Oh, I wanted the rate of change from 5 to 8. It's -6/3, so -2. And I wanted to flatten it out a little bit at the end. So 28 would have worked just fine, but it would have been in a direct line. And there wouldn't really be a reason to put the 9. So I guess the answer is aesthetics. Any questions? Comments? Snide remarks? Thinking in terms of the wider problem that we did yesterday. So another increasing, decreasing. Here our delta y is +6. Then our delta y was a massive +20. Then our delta y was -6. And then our delta y was a -1. So since we had different directions of the function, we see different changes in y. How's everybody okay? I get stuck picking numbers sometimes because I have to make sure that the numbers kind of like work out aesthetically for me, even though students generally don't notice when that happens. You ever had a teacher that like would write multiple versions of a test? That's kind of always my favorite, is when you write multiple versions of the same test. So everybody's doing a test on like factoring polynomials, but everybody has a different test and you don't know it. If your teacher didn't do this and then suddenly started doing this, that's because there are some students in your class that are cheating off each other. The teacher knows it and wants to find out what happens. And they don't tell you because it's more fun that way. Because then I just figure there are two students that are cheating. I know that are cheating off each other during tests. I just make sure that they have different versions of the test. And you just sit there and watch them when the test begins until they realize they're like, oh shit. And then my favorite is when the students are like completely unaware of their surroundings and like, oh, Professor Leach, are there two versions of the test? And I always just say, why do you ask? And like, and the friend's like, oh, dude, because they're completely unaware of their surroundings. And then it's kind of funny. My favorite instance of cheating happened in high school because there were two guys cheating off each other, but neither one of them knew what they were doing. So my old guys, you are terrible even at the cheating part. You can't cheat off of each other when neither one of you knows your elbow from a hole in the ground. And you could tell because one student had a very distinctive way of writing the number 9. He wrote a number 9, not just like American style with like a like plant the flag 9. He didn't write a 9 this way. Plant the flag, America. He wrote like, he hooked his 9s. Now, this is not a big deal, right? But the dude copying off of him wrote in all caps. And so when the answer was supposed to be like, instead of, it was supposed to be like 97, and other student wrote 97 with his fancy 9s, what did the other dude write to copy? Fucking G7. I'm like, are you fucking kidding me? The problem is supposed to come out to a number and you're over here writing G7? Come on, man. This is like the single most incompetent cheating I have ever seen. You can't see the G7. So G7. I guess what I'm saying is that when high school students are not very good at cheating. If you were in high school and you like cheated your way through high school and you think you're like real good at it, you're not. We always know. We always know. We just don't always worry about it. Anyway. I gotta erase that because if someone like is reading the notes later, they're like, oh, what is this weird 90s? What is 97G7? Is that some kind of secret code? And then students that aren't here today are like, oh, what was 97G7? And then if you were all cool, you'd be like, well, if you know, you know. And then the students that aren't find out, they're like Googling that shit. And then we could all see the Google search results if they changed. What happened at the 1997 G7 summit? Is there something going on there? I have a problem for you to do. Similar to yesterday's problem. Similar to yesterday's problem. But in setup, but different in yesterday's problem, because notice that this function goes up and down instead of just one direction. So you can help each other on this problem. So it is not possible to cheat on this one. So if you're looking to cheat on today's math problem, sorry, that's just not an available option. You're supposed to help each other. It's kind of like, I want to see an Olympics where there aren't any rules against like steroids. I don't know if I brought that up before, but I kind of want to see that Olympics. I want to see like what we can get out of a human being. How crazy can we make? How far can we get a human being? Then I want to try to genetically engineer a shot-putting human. That would be incredibly unethical, but I don't even know what that would look like. So please help each other on this problem. Also, I will be collecting this paper because I want to see where your thoughts are at. I need some more stuff to look at tomorrow when I'm supposed to be in meetings.